So I can rewrite the right-hand side as 5 to the third times x plus 6. Okay. Notice how I just rewrote it. I substituted in the value. I know that it's the same. Now my bases are the same. So since my bases are the same, all I'm focusing on are the powers. So now we're just focused on x is greater than 3 times x plus 6. Okay. So now we're going to go through the math and figure out what that is. So when we distribute, we get x is greater than 3x plus 18. We're going to subtract 3x. When we subtract 3x, we end up with negative 2x is greater than 18. We're going to divide by negative 2. Remember, when you divide by negative, it's going to cause your inequality to flip. So we divide by negative 2, so it's going to become x is less than negative 9. Okay, so we now know that it is x is less than negative 9. Is less than negative 9. Which means that our solution is from negative infinity to negative 9. Okay, so let's look at that graphically. What would that look like? Now, graphically to solve this, if you, you're going to have to kind of use a little bit of your imagination as far as seeing the lines. Not lines. No, we can do the shading. I'm tripping. Okay. So we have, we're going to go to y equals, and we're graphing the lines, like the linears, by the way. We're not graphing the exponentials, we're analyzing the linears. So we had, what did we have? X. We're going to put that in, and then we're going to put in 3x plus 18. Okay, so we're looking for when is x greater than 3x plus 18. So I'm going to hit graph. We're going to have to find their point of intersection. What did I put in? Yeah, I need to move it. So we can see down here. I was like, hold on, window. Let's go to negative 20. And there we go. I did it backwards on this one. I needed to change my domain, and I changed my range. Why? Because, just to keep myself on my toes, I guess. I don't know. Also could be because it's Saturday and up here working like a special person. All right, so you want to find the point of intersection. So to find the point of intersection, we're going to second trace 5. Yep. So there's my point of intersection. At this point, you're looking for when is x, and x is our blue line, greater than our red line. So when is our blue line on top? Well, our blue line is definitely on the bottom to the right, but to the left, it's on the top. So that's why it's from x is less than negative 9. That's when this is a true statement, okay? And so from negative infinity up to negative 9, this is when we're less than, okay? And that's what we would put. So that's your graphical example of it. Okay. All right. Next, we have 1/3. 2x plus 9 is less than or equal to 1/27 x minus 3. Okay. So again, we want to be mindful that 27 equals 3 to what power? If you said 3 to the third, you're a genius. Okay. So we know that 27 equals 3 to the third. Also, if we didn't want to work with a fraction, we know that 1/3 equals 3 to the negative 1, right? Okay, so we can rewrite this whole thing in a whole different format. So 1/3 is going to become 3 to the negative 1, right? Less than or equal to 1/27. So 1/27 is a fraction. So we already know that 3 to the positive third is 27. So therefore 3 to the negative third would be 1/27. So it's going to become 3 negative 3x minus 3. Our bases are the same. So all we're doing is focusing on our exponents. So now we have, I'm going to go ahead and distribute as I do it. So we have negative 2x minus 9 is less than or equal to negative 3x plus 9. I'm going to add 3x to this side. So when I add 3x, so I'm adding 3x. And I'm going to add 9 to this side, and I'm adding 9. So that's going to leave me with x is less than or equal to 18. So my solution is from negative infinity to 18 is what we got algebraically. Okay, so we're going to check it graphically. So let's go to our handy dandy Sylvie. So open Sylvie. I'm going to go here. And again, I'm putting in the linears, not the whole exponential. So we have negative 2x minus 9. We have negative 3x plus 9. And we're looking for less than. So we're looking for when this graph, my y1, is below y2. So my y1 is blue, my y2 is red. So I need to know when is red on top, okay? That's what we're analyzing when we look at the graph. I'm going to reset my window so you can see that I'm going to do all the zooming and setting and changing with you. So I graphed it, it's graphing. And I know it's done graphing because that little yellow dot's gone. I can't see where they intersect. So I'm going to adjust my window so that I can see those intersections. I'm going to go to window. I'm going to make everything a little bit bigger. I don't really think I need to change my X. Let's go to 30. I do not like a lot of tick marks. I'm just going to change that. I'm going to go down to negative 30. I'm going to go up to positive 30. And again, these little tick marks. So I'm going to hit graph. See if my changes help me see a point of intersection. And I'm like, I still don't see nothing. Oh no. So I'm going to go back to the windows, and it looks like my range values are enough. Not enough. Now, the other option is when you're in Zoom, there's this little special thing called Zoom Fit. If you arrow up or press, it's Zoom 0. But Zoom Fit, sometimes it'll do the work for you. It's like, okay, let me see what I can do. You've done what you can. Let me see if I can help you out. And Zoom Fit, look, it helped me out. It found where I could see the intersection. So I'm going to hit second, trace, 5, enter, enter, enter. And it says at 18. So we already knew that. We got that part right. We're geniuses. So now I'm looking for when is my y1 less than my y2. So my y1 is blue. When is blue below red? Blue is below red to the left, which is right here, less than 18. So when my X values are getting smaller, that's when blue is below, which is why it's negative infinity to 18. And because it says equal to, that's why we include the bracket. All right. Okay. Up next. So we'll have some more properties to look at with logs in particular. So we just did exponentials. Now we're on to logs. So if b is greater than 1, so the base of your log is greater than 1, then that means that your log base bx is going to be greater than log base by if your x is greater than y. All right. So what this is just saying is that if you have your log, it's just doing this, right? Is it go forever? Excuse me, that's what number one is saying. Okay. Number two, I'm going to change colors for number two. It says if b is between 1 and 0, and log base b of x is less than log base b of y, then x is greater than y. Okay, so now instead of it going, we're now saying that it's going to be doing something like this. I don't know why I feel the need to like actually get as close as possible to asymptote, but I really can't tell you. Go figure. So this is what 2 is saying. And this is also true for when it's less than or equal to. Okay. Next, if the log base b is between 0 and 1, then log base b of x is greater than log base b of y, then x is less than y, also true for y. Oh, because you can, when you do reflections and it goes across the other side. Okay, cool. Makes sense. Because it could be reflected and be doing that. Got it. All right. So there's another direction your graph could go. So 3 is saying if you are so now it's going up and your values. Got it. Okay. So first we have find the solution of the inequalities. So log base 9 is greater than 2 log base 2x. And again, here we want to apply our log properties that we know. So we're going to make our power into and our coefficient into a power. So now we would be working with log base 9 is greater than log base 2x squared. Okay. Now that our log bases are exactly the same, there's no lingering coefficients in front. All you're now focusing on is your arguments. So our arguments are 9 and x squared. So we're looking for when is 9 greater than x squared. Okay, well, this one you can really easily solve by itself. You take the square root. So that gives you plus or minus 3 is greater than x. Okay. What that means is that when we look at our graphs, we're actually going to be graphing the logs. Unlike the exponentials where we only graph the linears, we're going to be graphing the logs here in a second and analyze where they're at. Okay. So here for one of these is true and one of them is not. So remember we talked about that negative or whatever. Well, it could even be a negative. So we know that the -3 is our extraneous, right? That's our extraneous option. So we're looking only at when x is less than 3 is our answer. Okay, it's the non-negative answer, so therefore it's our answer. Okay, and then we got to also keep in the fact that logs have restrictions. So we're looking for when x is less than 3, but it can't go too far, right? It can't go past 0 because of the asymptote. So keeping that in mind, we now know it has to be between 0 and 3. Okay, so between 0 and 3 is where it can take place. Now let's look at it graphically. So again, unlike exponentials, we're actually putting the log in the calculator. So we're going to put log base 2 9 as our first one. And we're going to put the log base 2 of x squared as our second one. Okay. And we want to know when is our log base 2 of 9 greater than log base 2 of x squared. So we're looking for when is, in this case, our blue above our red, right? So we're going to hit graph. Oh, let me stop the graph. Anytime you want to stop a graph, you press the on button and it stops it. I'm going to reset my window so it could be at the regular home window and we can go from there. Okay. So notice that my blue is just a it's just a number because it has no variable. All right. And it says we're looking for when is the blue above the red in our case of our problem. Well, blue is only above the red, right? On, how did I put this in? Oh, sorry. Sorry. I should have graphed it as 2 log base 9. I meant 2 log base instead of 2 the square. That's what I have in my notes. Is that right? I hate when I do that. Just graphing the original. Sorry. Here we go. I was like, wait, it's not what I had in my notes. Don't worry. There it is. My stretched. Okay. For solving, that's why we did that. But actually looking at the graph, you can see here that because of our asymptote, we're not going to pass. And so we go as far as 0. That's when it's above the red. And then after that, the red encompasses it. Okay. And our point of intersection would be second when trace by inner. Arrow over. And it's at 3. So 3, and it's the left of 3 is when we are above. That's why it's there where it's at. 3 is greater. And again, we have the asymptote that prevents it, so it doesn't matter what happens into the negatives. Okay, on the next one. So on the next one, again, you can solve it by hand. So we're going to show you how to solve it by hand and go from there. So first, by hand, we want to get rid of the log. That's what we want to do. So in order to get rid of the log, we have to use the base. So we're going to raise everything to the second. This is going to cancel this out, and we're going to be left with 2x plus 1 is less than or equal 2 to the third, which is 8. And now I'm just solving this. So then I'm going to subtract 1, and we get 2x is less than or equal to 7. And then I'm going to divide 2. And we get x is less than or equal to 7/2, right? Now, this is just one side of it. We also have to remember that there is an asymptote. So because of that asymptote, we have to remember that all of our arguments have to be greater than 0. So whatever the argument is itself has to be greater than 0. So 2x plus 1 has to be greater than 0. So 2x plus 1 has to be greater than 0. And therefore, when I solve this, we get that x is greater than -1/2. Okay. And this is because of the vertical asymptote. Okay. I guess I should have pointed that out here, but this has to be, but I didn't. My bad. It's on me. I'll take the blame. But your argument has to be greater than 0. So we know that. All right. So now putting these two together. So x is greater than -1/2, but less than or equal to 7/2. And that would be our answer. Now, when it's not pretty numbers, it may not be as easy to see it graphically. So that's another reason why it's good to be able to do it algebraically and have that as your background knowledge so that you know what you're looking for. So when I go over here to graph, I'm going to actually put it in my log base 2 math arrow up, log base 2, what was it? 2x minus 3 minus 3. And we have 3. And we're looking for when does this happen? So again, I'm going to go to graph. Let it think. Okay. Pew. And there's its point of intersection. And then the other thing is, where's my asymptote? So like you can kind of see where it's approaching. If you can't tell the asymptote, that's what your table is for. So if I go to my table and I'm looking at my values, I'm trying to see where is it getting closer or what values am I approaching. You would have to change what you're counting by, but it's doable. The other thing is you can go to trace. Am I on the blue graph? I want to be on the blue. So if I'm on the blue and I'm tracing, where am I came up with it. There we go. You can kind of see like where your values are approaching or where it's coming from. So notice how my X right here is at 1.5. And if I go further, it shows nothing. But when I get back to the 1.5, it's like, hey, this is where we're at. Okay. You can kind of gauge it from there, I guess would be my guess. It's kind of seeing where your X is, where that asymptote is. I don't know why it's not showing it a very good example of 0.5, but that's another reason why the algebra is important, because you can mathematically support it as to where your boundary is. You also can just find your boundary by doing the inside of your argument, because that's how you know your asymptote has shifted. But anyways, so my thing is being weird, like super weird. Second trace 5, intersect, intersect. So we're at 5. 3.5. Where'd he go? How did I get? Uh-oh. I don't know why it's intersecting at 5.5. I'll get that. Hold on. Hold horses. Why? Oh, that's why I made up a whole thing, guys. I was like, I'm not sure why this is doing this. I thought I was going crazy. I am. It's called being at work on a Saturday because nothing was making sense. I may have to actually, edit that out. No, I'm not. Y'all are going to see my craziness. All right, now we can see where that half is at. I'm tripping. And then second trace 5. And now we're at 3.5. I was like, man, again, use the technology to ensure you're correct. Do your math as your saving grace. But now you can see I'm at 3.5. And then I was looking for when it's less than, and it's less than to the left. And again, we have that asymptote. So if I'm tracing the blue, you can follow that it's going. I was like, I didn't know when I was going to get there, guys. It's going. And then it's off the page. But notice it disappears kind of like right here at negative 0.45. And then for what, I can't get any closer in on it, but you can zoom in and you can see it and you can analyze the table, changing your table values. So like if you wanted to change it, so you see that it has to be smaller than -1 because after that, things get real funny. You can go to table setting and you can start and you can decide what you're going to count by. So let's say if I counted by 1/4, right? I'm going to go back to the table. I'm going to look and see what happens as I'm counting by 1/4. Dun, 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 dun. See, at -0.25, I'm good. But what do you notice here at the 0.5? Error. Okay. All right. So keep that in mind. Our last one. Our last inequality we have here. Might as well go big or go home, right? Notice that their bases are the same, okay? Because their bases are the same, and that means that our arguments have to be equal to each other at some point, right? They're going to equal at this point, at some set point. That point is their point of intersection. So you can find the point of intersection, and then keep it in mind that your argument has to be greater than 0. So like finding all those things is gonna narrow down to what your x can be in order for this to be a true statement. Uh-oh. Uh-oh, I don't know what I did. I swear I pressed keep. Oh, I was like, oh man. Good thing I hadn't written it. Okay, back into this natural, unedited Saturday teaching. So again, bases are the same, check. So all now is focusing on the arguments. So looking at my arguments, they're going to intersect. That point of intersection is going to be one of my restrictions for when this is true. So we're looking for when 2x minus 3 equals x plus 5. Okay, so 2x minus 3 is going to equal x plus 5 where? Well, no, sorry, should be, that's not true. Then equal. Should be still greater than or equal to. Yeah, it should be. It's going to be, when is this true? When does this happen? Right? Okay. Trying to think, because they're halves, so they're going to be coming down this way. It should be the we'll see. My brain isn't braining. I'm going to subtract x. So when I subtract x, cancels it on the side. I'm going to add 3, then cancel on that side. So we're left with x is greater than or equal to 8. But we're going the other way because that's what that note was saying. Got it. When it's between 0, b, and 1, your log, when it's greater than, it's going to be, okay. I know, understand why I wrote that note. So this right here would be true if the bases were greater than 1. So if bases were greater than 1, then this would be 100% true. But now I know why I made a note to myself to tell you to treat it as you're finding the point of intersection and then go from there. So treating it as equal to, and then that lets us know that this is where they're going to intersect at. And we'll analyze it from there. Okay, so that's our intersection. And then we're now going to this argument, 2x minus 3 has to be greater than 0. 2x minus 3 has to be greater than 0. So focusing on that. And we get that x, we're going to add 3. We're going to divide 2. And it was positive 2, so it doesn't change anything. So we get that x is greater than 3/2. All right. So we know that it's going to intersect at 8, but an x has to be greater than 3/2. So putting all what we know together, we then and therefore can come to the conclusion that if x is greater than 3/2 and it's going to intersect at 8, then 8 has to be where it stops at. It's going to be equal at 8, and then therefore everything else has to take place. So following that logic, let's make sure graphically that's true. And again, it's because it's the b is less than 1 but greater than 0. Why this just kind of got turned around in my head. So if I go to y equals and I put in log 0.5, and then we have 2x minus 1, no, minus 2x minus 3. Then we're going to come down here. I'm going to math, up. We're going to put in log base 0.5. And we end up with x plus 5. Okay, so the reason why we're focusing on the 2x minus 3, when you see it, it's going to be the one that's graphed furthest to the right. It's asymptote. So this graph is the one restrictions that we have to pay attention to. Because the red is coming towards it. The second one is coming towards it. So we're asking ourselves, at what point is the blue above the red? And the blue is above the red only from this window, from where its asymptote is, up until where they intersect. Okay? So this is what our boundary line. I can't go past this, because if I go past the blue, if I go past there, blue's asymptote, it doesn't exist. Okay. You could also have did it for found the asymptote here, and then realize that, okay, if I do the asymptote of this one, it's not going to be, it's going to be further. So that's why I'm going to focus on 2x plus 3 needing to be greater than 0. Okay. If it helps you just deciding which one of these to use, you're going to use the one that consumes both. Well, consumes both graphs. And yeah, that concludes our lesson. Now I'll have to take a